So whenever we're given sort of a word problem, it helps to introduce our own variables, introduce our own notation. Okay, so we'll make some blocks. We'll call this X, Y, and Z. We'll name the length, width, and height of the box. Whenever you're setting up these kinds of word problems, it's very important to state what units you're using. Right? So here, we've said length in meters. So we'll always specify that little bit of information. So we'll give a name for the volume of the box. Units there will be meters cubed. And then we'll define the surface area. So if we've got a box like this, we can calculate the surface area by adding up the area of all the sides. Okay, so for each pair of variables, we've got a face. We've got X, Y. That'll give us a plane here, but also a plane on top. For X, Z, plane on the side, plane on the other side. Okay, so we get two copies of each pair of variables for our surface area. Doing optimization, it helps to frame mathematically what you want to do. Minimize the surface area subject to the constraint that the total volume is 1. So far, so good with that? So I'll show one technique for optimizing with constraints. So we'll do one before the break, and we'll do another technique after the break. So one technique is to notice that we've got a 3-variable problem here, right? But we've got a 2-variable test. So we've got one too many variables here. So what we'll do is we'll reduce the number of variables. So let's get rid of the variable z. So we can divide that out. And now we can write our surface area function just in terms of x and y. Two-variable function. Okay, so now our tools of multivariable second derivative test will apply to this two-variable function. One thing to notice about these critical point calculations is that we often wind up with several equations that we need to satisfy simultaneously. Okay, so we need to find x's and y's that will make this true at the same time. So we can rewrite those equations following way. Rearrange, divide out by 2, we get here. Okay, now substituting in this y here, we get right, so that's the result of taking this equation for y and plugging it in. Yes, question?
We do that to have multiple equations at once.
Yeah, so this is substitution, right? We're taking one variable, substituting it into the other variable, or into the other function. Okay, so we want the solutions of this fellow. So we have two solutions, either x is 0 or x is 1. Okay. Now we've got two options for our critical points. Let's start off with x equals 0, then we get total volume 0, which is not admissible. We need total volume 1. If we take the other solution, x equals 1, plug that in here, we get y equals 1. Then we can plug both of those in, get z. All right, so we'll use our equation for z. So that'll satisfy our constraint at least. That'll give us a box of total volume 1. Okay. And this is sort of a nice solution to the problem, right? We want to minimize surface area so we get this very nice symmetric object, right? All the lengths are the same. Okay, so this seems like a good candidate for being a minimizer. Now we'll check that it's a minimizer using the Hessian. Right? So we'll check that this is actually a minimizer. So we'll calculate the Hessian of surface area. Right, so we go back to our first derivatives over here. We'll take the derivative in x. Taking the derivative in x, we get 4 over x cubed. Taking the derivative in y, we get 2. Derivative of this guy in x will give us 4 over x cubed. Derivative of this guy in y will give us 2. Clairaut tells us that we can copy this 2 to here. Okay. And then we get 4 over y cubed. Okay. So far, so good. Okay. Now we can plug in our critical point. This will have positive determinant. So this will be a min. Questions or comments about that example? Yes?
Yeah, just go back to when you decided to reduce the number of variables in your
Yes.
surface area function.
Yeah, perfect.
So when we had SA equals 2xy plus 2yz plus 2xz, that's just a function that can take on any volume, right? And then you decided to reduce the variables according to your restriction equation.
Yes. So we did this because we only have a second derivative test for 2 variables right now. And our original equation for SA has 3 variables. Right? So So we needed to go from 3 to 2 somehow.
Okay, but so is that true in general, that if you have a restriction equation and then you isolate one of the terms in the restriction equation, then if you then you're turning SA into a function that only satisfies that restriction equation?
Yes, so in general, you can take a constraint and use it to drop down in dimension 1. So you can use a constraint to go down 1 dimension most of the time. We'll also handle, after the break, we'll handle another technique for doing constraint optimization.
And in terms of how the SA function changes, like you had some SA function with a very big image, right? And then you're reducing the image to only the ones that satisfy volume equals 1.
Yes, yeah. Nice, sweet. Are there observations there, questions there?
What if the question told us to maximize the surface area?
Aha, yeah. So, right, so if we had to maximize, that's kind of a neat physical thing. Right, so if you think about maximizing the surface area of the box, right, that's sort of the opposite problem of minimizing. Right, so the minimum, we get this very nice, very symmetric box. But for maximizing, make a very, very, very long, very, very thin box and still have volume 1. Right? So if we wanted to maximize, we could get bigger and bigger surface area. So so there'd actually be no maximum surface area satisfying the volume constraint. Neat. Yes?
So it would just be infinitely long and infinitely thin?
Yes. Yeah. Yeah. So there's so yeah, you'd get this kind of infinitely thin box, but it'd have huge surface area.